All right, we're going to continue on with the part 2 of section 9.3. And in this one, we're going to actually now put it all together and we're going to do a t-test for the mu. We're going to do a one sample t-test for the mu. Okay, so let's go ahead and go to page 591, go to 592. Okay, we're going to have in the green box, it says the one sample t-test for a mean. And it shows you the the test statistic there, the standardized test statistic, and then the Haas, a different type of Haas. You can have 3 types, right? Greater than or less than, these are both one-sided, and then there's a not equal to, which was a double-sided, okay? So let's see if we can do example number on the example on page 592, which says healthy streams, okay? The level of dissolved oxygen in a stream or river is an important indicator of the water's ability to support aquatic life. A researcher measures the dissolved oxygen level at 15 randomly chosen locations along a stream. Here are the results in milligrams per liter. An average dissolved oxygen level below 5 milligrams per liter puts aquatic life at risk. Okay. A, do the data provide convincing evidence at the alpha equals 5% significance level that the aquatic life in this stream is at risk? In other words, is the dissolved oxygen less than 5? Okay. So how would we do this? So let's go ahead and, first of all, so this would be the example here, and we're going to do the, what? We're going to do the state. We're going to state, right. A, state what? What are we doing here? Our HO is going to be what? Our HO is going to be that the dissolved oxygen level is equal to 5. Our HA, what we're trying to prove is that this guy is going to be less than 5, right? If it's less than 5, right? And then what? Ooh, okay, our alpha was 1%, I think. Alpha was 1%, was it? Or 5%? Alpha, oops. Oh, it's 5%. Alpha is 5%. Alpha is 5%. And, okay, so so let's go ahead and check our conditions. Number 1 is it's a random sample because we did 15 random samples at different places in the stream. 2, we did not oversample. Oops. So we're good here. Large counts. N is less than 30, unfortunately. So we have to do a dot plot to make sure that there are no skewedness or anything like that. And we actually, in the book did a histogram. Okay, we did the histogram. And it shows no skewedness or no outlier. So we're good to go. Okay, so let's actually do this. So we're actually going to do it now. The T statistic is going to be whatever we found here minus this guy and this. Okay, so we put our 15 things into L1 and we find the X bar and the S of X, and we find what? X bar was 4.77, so we get 4.77 minus this guy here, 5, and we found the S of X, the standard deviation of the sample, to be 0.9396. And we sampled 15 of them. This is what we do. And if we do that, we're going to get negative 0.94. We get negative 0.94. So that's our test statistics, right? So so we're going to have to go to table A. We can go to table A and B. I'm sorry, table B. Go to table B. And if you look at table B, and we're trying to find 0.94. If we do that, what do we find? It's between 15 and 20%. We're going to find a p-value of 15 to 20%. Okay, so what does that mean? Our p-value is larger than alpha. Our p-value is larger than alpha. So we what? We failed to reject the hoe. We do not have convincing evidence for the ha. Okay? So we do not have convincing evidence that the dissolved oxygen level is less than 5 milligrams per liter, thus endangering the aquatic life. Okay? B, given your conclusion in part A, what kind of mistake could you have made? Could I have made a type 1 or type 2? Well, I failed to reject, right? Which means that I, by definition, I can only make a type 2 error, which is where when I am not to, I'm supposed to reject it, but I failed to reject it, okay? Which means that actually it is this, okay? We do have a dissolved oxygen level that is less than 5, but I failed to reject it, okay? Explain what this mistake would mean in the context. So, in other words, the dissolved oxygen level is less than 5, but I failed to detect it. In other words, I have a stream that is not good for aquatic life, but I'm going to think that it actually is okay for the aquatic life, therefore endangering the aquatic life in that stream. Okay? And on page 594, it tells you in the technology corner how to actually do this step, this entire thing in your calculator. So you would go to stat and tests and go to t-test. The t-test, you're going to say, you're going to input, you're going to input the stats, you're going to input the data, right? Because you inputted the data already in your L1, all right? And then you're going to go ahead and your mu is going to be equal to 5. You list, the data list is L1. And then the mu is going to be less than mu naught. Okay, and then you go ahead and plug and chug, and you're going to get the results. And you're going to get a t-value, you're going to get the appropriate p-value, and from there. Okay, and then you can draw your conclusion. All right. Now let's go to page 595. In 595, it talks about the relationship between a two-sided test and the confidence interval. Okay, so and when you're doing a two-sided test, and only when you're doing a two-sided test, you can use the confidence interval to do a significance testing. Okay, you can use the confidence interval that we found in chapter 8.3 to do a significance testing. Okay, so you go to the middle of page 595. There are two bullets there. Okay. If a 95% confidence interval for mu does not capture the mu naught, okay, then we immediately reject the hoe. Okay. The next one says that if the mu naught is captured, then we would fail to reject the hoe. Okay. So let's see if we can do this in an example. Okay. So let's do the juicy pineapples. Okay. On the bottom of page 595. At the Hawaii Pineapple Company, the mean weight of the pineapples harvested from one large field was 31 ounces last year. Different irrigation system was installed after the growing systems. Managers wonder if the change will affect the mean weight of the grown in the field. To find out, they select a weight and random sample of 50 from this year's crop. A, state an appropriate pair of hypotheses for significance testing in this testing. So you're going to find the hoe to be what? Your hoe is that the mu naught is equal to 31. Okay? The ha is that the mu naught is not equal to 31, therefore setting up a two-sided test. Okay? Be sure to define the parameter of interest. So what is the parameter of interest? See, so the mu is the true mean weight of all the pineapples grown in the field this year. Okay. B, check the conditions for performing the test. It's a random sample, so we're good there. And we're going to assume that there are many, many more pineapples than 310. So that's good. The large counts. N is greater than 30 because we sampled 50 of them, I believe, correct? 50 of them? Yeah, so we're good there. Okay? So C, a 95% confidence interval for the mean weight of all apples grown in the field was 31.255 and 32.616. 31.255 to 32 point, what? 32.616. 32.616. Okay? So, again, this is our confidence interval that we did with a 95% confidence interval. If we do that, we see that the 31 here is not captured within our confidence interval. Therefore, we can reject the whole. We can reject the whole, and we say that we have convincing evidence that, yes, it is not equal to 31. Okay? So that's how you'd run that. Let's see, D. There's a D here that we need to talk about. D. Can we conclude that the different irrigation system caused a change in the mean weight of the pineapples? Okay, here we go. We're talking about causation here. Now, can we say that it was strictly because of the new irrigation system? Well, no, right? There could be several different things, right? We could have had more sunlight. We could have had, I don't know, we could have had a lot more rain, which would maybe make them grow larger. Who knows, right? So, because we did not do an experiment to actually establish causation, right? Okay, and we'll stop here today.